So let's talk about memory address. Memory is an array of bytes within RAM or memory. It's kind of like a street. So this is the street. A memory block is a single byte within memory. It's kind of like a house on a street. And the house is used to hold some value. So it could be stuff in the house. It could be like a stove or a person or a couch. Then there's memory address, which is the address of where those bytes are stored in the RAM. So this is the house address. So we've got a street, which is the memory. We got memory block, which is the house on the street. And we've got an address of where that house is on the street. So let's get right into it and create a variable here. Let's do a little game variable. We got a username. We'll name him Wizardman. Wizardman's level is 34. And let's check if he's a wizard or not. If he's a wizard, it's true. If he's a wizard, it's false. So standard console output. Let's just check where, let's check where the username is stored. And we use that with the AND operator. So if I were to run this, this is the address in hexadecimal that's sitting in my RAM card right now in the memory, showing that in the memory, this is where this username, Wizardman, is sitting. And I could do the same thing now with the level and the Boolean. So now we can see that all three of these are kind of sitting, username and level are both sitting on the same street, but now this one's got an E in front of it. This one's sitting on probably a different street, but these are like right next to each other kind of in the memory. If we were to change these into integers, let's say 1, 2, and 3, integers only take up 1 memory byte per integer. So if I were to print this out now, let's make some new names for it. 1, 2, yeah, it looks like they're right beside each other, but they're spacing each other. They're spaced out by about 4 bytes each. So whatever, it doesn't really matter that much, as long as you understand the concept. Now let's move on to pointers. A pointer is like a variable that holds a memory address to another variable. So as we know, the at shows the address. Now we've got another operator, the indirection operator, which shows the value at the address. So let's bring Wizardman back. And instead of checking whether or not he's a wizard, let's go ahead and add an array of strings, such as like spells. What kind of spells can Wizardman use? He can use a fireball, he can use arcane missiles, frost shock, and chain lightning. So now let's create some new variables. One is where we're gonna create it with a star. So the star means we're referencing a point, something that's pointing to the address of something. So we're gonna name this, start it with the P, lowercase p, then uppercase username. So this is referencing this. And it's not referencing it yet. We haven't assigned it yet. This is just a naming convention. Anytime you use pointers, you got to start the first letter with a P, and the second letter has to be the first letter of whatever variable or name you're referencing as a capital letter. So we're going to assign this to @username. And as you know from the memory address, this means the address of this memory. So it's pointing, this variable here, all it is pointing to one of these numbers down here. That's it. It's just assigning itself automatically to one of those numbers. Now let's do another one for level. Now instead of typing in level, we're going to do star p level with the capital L. And we're assigning it to the level address. Then one more, we'll do string p spells, and we're going to be assigning that to the address of the spells array. And we'll go ahead and print out the pointers. Oh, since it's an array, we have to specify that it's an array. So we could say like 1, let's say. So this is pointing to the memory address of it. So this, let's say this array is pointing to one of these numbers and asking one of these numbers what the value of it is. So it's not printing out this, it's just printing out what the value of this pointer is. Which brings us to say, what if this doesn't point to anything? How do we know it's actually working? And one way to do that is by using something called null pointers. Null, let's talk about null. Null just means nothing. empty value. So when a variable or a pointer isn't holding anything, then that means it's a null pointer. And it's typed like this, null pointer for short. This means a pointer pointing at nothingness, empty nothing, a void, just pointing at like empty space. Why would you use a pointer that points to nothing? Well, it's helpful for determining if an address was successfully assigned to a pointer, but null pointers can also cause issues with pointing to free memory and using up RAM or causing random errors or memory leaks. So let's create a pointer here. We'll do pointer to null pointer, and we'll create an integer, just integer a at 1, 2, 3, pointer at a. So we want this pointer to just point to the address of a, and if the pointer equals null, so we just assign this pointer to this address, right? We want to make sure that this line worked. What if this line didn't work? What if this line still isn't pointing to a? Because if we didn't do this, it would be pointing to nothing, but we're pointing it to a. So it better be pointed to a. So if this pointer is null, that means that this didn't work. And if it is null, then we'll return address was not assigned. Else, if it's not null and if it's anything else, that means the address was assigned. And then we're just going to return the pointer as well. So let's hit run on this, and it says address was assigned, and this is the value of that address. Now if I were to delete this line and hit play, it says the address was not assigned because we don't have it assigned to anything. We have it assigned to null pointer, which is nothing. So dynamic memory, memory that is allocated after the program is already compiled and running. So this is kind of how we can use an operator called, so new is a function that allocates memory in the heap rather than the stack. This is a bit of jargon. It's okay if you don't understand it, but heap is when the memory is used by all parts of the app, whereas stack is when memory is used by just a single part of the execution. So this is useful when we don't know how much memory we will need, and it makes our programs more flexible, especially when we're accepting user input. So let's say we have a pointer pointing to a number, and the pointer value is null, it's nothing. Instead of us giving the pointer a value and pointing it to an address or anything like that, we're going to assign it to new int, which means this is an int that we're creating, but it doesn't exist yet, and the pointer is actually creating the int itself. So when we're creating an int, we also want to delete it after we're done, but we're not done with it yet, so we'll do that in a bit. So now we're going to assign pnum to value, let's say 31, and then we'll do console output to the address, and we're going to grab the address of pnum with the @ and then we're going to grab the value as well with the start pointer. And before we run it, we're going to want to delete after we've created it because we're done using it. So let's do delete pnum. So you do this because when you create the new pointer and it automatically assigns it to a value with new, it uses the pointer and stores it in the memory, and it's going to create memory leaks and use up unnecessary RAM for things that it doesn't need to. So always just delete it because these can add up after a while, and if you never delete them and you have a whole bunch of them, then you're going to have a poorly optimized program. So it's best practice to always use delete after you use new, as soon as you're done using it. Recursion is a programming technique where a function invokes itself from within. It breaks a complex concept into repeatable single-step processes. So what's the difference between iterative and recursive? Remember iterative from the last video? This was when we would sort a bunch of random numbers or we would search through a bunch of random numbers, and we would have to use nested loops for it, and we'd have to do like int I equals 0, and then inside of that it's like int j equals 0, and like a whole little equation just to sort through all the numbers. Well, recursion or recursiveness is pretty much when we're doing that, and it uses less code. It's cleaner, so it's really useful for those searching type of algorithms, so we don't have to use a bunch of nested loops. The disadvantage is it uses less memory, or sorry, it uses more memory, and it's slower. So let's do like a walking function for a video game or something. So we got void walk int steps. And we'll put this function right outside our main block. So we'll do walk 100 and we'll get this big block out of here just to keep it clean. And then we'll create the function right after the main block again. So int steps, and our steps are going to be if steps are greater than 0. We'll do standard console output. And we're going to do 1 step. And we'll do walk steps -1. And if we run play, we get about 100 steps. So that was a lot faster way of getting 100 steps than when we had it before, when we were running it through iterative loops. Now we got to be careful with recursion though, because we can run into something called a stack overflow, an infinite loop. So if I were to delete that, and I were just to do walk steps, and wait, hold on. I want to keep that, and then I want to get rid of -1, and it's greater than 0 sign. So if I were to hit play, this is just going to keep running on forever. So this is running, and let's cancel out of that because it's just going to keep on going. So see, it's spinning it out like a million times. This is what's called a stack overflow. That's what it means when you trigger a function and you add something called a frame to the stack. When your stack is overloaded with an infinite loop, you'll create a stack overflow. So that's a problem that can happen with a recursion. Same with like the while loops. When you get into those infinite loops. Now let's talk about structs. Structs are a collection of related members, aka variables. They can be of different data types. They can be listed under one name in a block of memory. They're very similar to classes once we get to object-oriented programming, that probably in the next video. But there's no methods to it. It's just the attributes part of classes. So structures are a great way to make items or players even for video games. So before this int main, let's create a struct player. We could do standard string player name, and then we can do the level, and we can check whether or not the player is online. So let's do player 1. So we're initiating player 1 right now as a struct. So this is the struct. This is the name of the struct that we're going to give. And now we're going to fill out the values of this struct. So player 1 dot player name. This player is going to be named Chuck. Player 1 dot level. Chuck's going to be level 5. Player 1 online. Chuck is online. We can create a second player as well. So we could do player 2. Player 2, I'm just going to copy and paste this. Player 2 is Abe, level 12, but he's not online. So Abe better watch out because Chuck is online and he's catching up. So standard console output, player 1 dot player name. So we're just going to print out all of these variables. We're going to print out the level, the online. So if we were to hit play here, I think it just didn't finish loading up yet. What's happening here? There you go. I think I just had something loaded into my cache. The compiler didn't like it. Anyways, just waited a couple more seconds and now we can see we got Chuck, level 5, he's online. We got Abe, level 12, he's not online. So this is all about structs.